Good afternoon. I am Frances Hellman. I'm professor and chair of the physics department here at Berkeley, and I'm delighted to welcome you all to the annual Emilio Segre Lecture. This lecture is put on every year by the physics department and is made possible by the generosity of the Raymond and Beverly Sackler Foundation. Before I go any further, I want to remind everybody to please turn off your cell phones. And also to point out that this lecture is being videotaped, and we would ask that questions be held till the end. So at the end of the lecture, we'll have time that people can ask questions and so forth. But please do hold your questions till then. So I want to start by telling you a little bit about Emilio Segre. As most of you, I think, know, he was one of our very esteemed faculty members. He, together with Owen Chamberlain, won the Nobel Prize in 1959 for the discovery of the antiproton. He was a student of Enrico Fermi's in the late 20s and later was a professor in Palermo. I had not even realized this story before, but apparently while he was on a visit to California, Mussolini passed a law barring Jews from university positions. So Italy's tragic loss or tragic short-sightedness was America's gain. As he was unable to return to his home country, he became a group leader for the Manhattan Project at Los Alamos National Laboratory and eventually became a professor here at Berkeley shortly after the war in 1946. Segre is known as one of physics' greatest experimentalists, and this lecture has a tradition of inviting the world's greatest experimentalists to come speak to us. He's a figure we look to from sort of the start of what's an era known as big science, which really started here at Berkeley with Ernest Lawrence. The Bevertron was built. It was overseen by Segre and Chamberlain's research groups at what was called the RAD Lab, the Lawrence RAD Lab, in order to observe the antiproton. If he were alive today, Segre would no doubt have been part of the Large Hadron Collider, which you're going to hear about today, its creation and its operations. So it seems particularly fitting that we are hosting today Peter Jenni, who's been part of the LHC, the Large Hadron Collider, for so many years. So Peter Jenni was born in Switzerland in 1948. He obtained his diploma for physics at the University of Bern in 1973 and his doctorate at the Swiss Federal Institute of Technology in Zurich in 1976. He participated in CERN experiments at the synchrocyclotron, at the proton synchrotron, and at the intersecting storage rings. He was a staff member at the Stanford Linear Accelerator, SLAC, and became a CERN staff member in 1980. In the years since then, he's worked actively on building the Large Hadron Collider, but he was also very actively involved in what was called the UA2 experiment, which I'm told was in direct competition with the UA1 experiment, at the collider, where he was majorly involved in the discovery of what are called jets, which I think you're going to hear about a little bit today, at least a little bit. Those jets were sort of the first very strong evidence for what is now the accepted theory of strong interactions called QCD, quantum chromodynamics, which won a Nobel Prize for David Gross, David Pulitzer, and Frank Wilczek. He was also directly involved with the discovery of the W and the Z, which also won Nobel Prizes. So since 1984, Peter has been dedicated to the planning and the building of the Large Hadron Collider. His main activities were focused on his being spokesperson of what was called a proto-collaboration. Then he became co-spokesperson and then spokesperson of ATLAS, one of the two experiments that made such exciting news this past summer by the observation of what we all think is most likely the Higgs boson. Today, the ATLAS experiment has some 3,000 scientists with 174 institutions from 38 countries, so you can imagine the job of being spokesperson of this enormous operation. Peter was reelected several times and just very recently retired from this duty, but retains a very strong involvement in both the operation and the physics of the experiment. So the announcement of this past year of the observation of a new particle, which, as I said, it's I think referred to not up there, up in the, when we get back to it, the Higgs-like particle, we believe is going to provide the long-searched-for key to the question of the origin of masses of all the elementary particles, and that's what you're going to be hearing about today. So this afternoon, Peter will tell us about the hunt for the Higgs boson and other results that have been obtained from the LHC in the past few years. And I'll conclude, we are very honored to have Dr. Jenni here today and very excited to hear the news from CERN. So let's thank our speaker.
So thank you very much for this kind introduction. And it is really a pleasure for me to talk today about the LHC project, the hunt for the Higgs boson, and also for physics maybe beyond the standard model. It's a great honor for me to talk as a Emilio Segre lecturer. In fact, personally, I have never met, unfortunately, Emilio Segre. This is the gang which found the antiproton, and I would like to just say at this occasion, the PhD student on the experiment was Tom Ypsilantis, and maybe like today, PhD students actually do a large part of the work. And I have been very fortunate to work with Tom for several years in one of my first experiments where I made my PhD. You can see this was a very simple scattering experiment in the mid-70s. So today, I will take you on a tour of the Large Hadron Collider project, which is really a very large global science adventure. It includes the accelerator. It includes a very sophisticated distributed computing system, and of course, the experiments. And all this was initiated more than 20 years ago, and I'm really very pleased now to report about first results, report about the first very big discovery which we could announce this summer. Now let me step a little bit back and give you also an overview of the history of the project, and maybe I start with a very naive motivation of the LHC project, which started in the early 80s. And in fact, if one would have to take just one transparency, I would take this one probably. This shows you on a very nonlinear scale the history of the universe from the Big Bang to today, some 13.7 billion years. And what we reproduce with the LHC in a laboratory, in a very small scale, are energy densities which correspond to just 10 to the minus 10 seconds after the Big Bang, when we collide proton-protons, and maybe something like 10 to the minus 5, 10 to the minus 6 seconds after the Big Bang, when we collide heavy ion nuclei in the machine. So if we look at this connection between particle physics and the cosmos, one can, for example, look at the ruler, which has the length of the size of the universe, 10 to the 28 seconds. Human scale is very conveniently in the middle here about. And on one hand, what we investigate in physics is what really goes on the large scale in the cosmos. And on the other hand, and that is our business, and that's what we were dealing now today, is looking at the smallest distances, typically at the elementary particle, which are the quarks inside, for example, a proton. Distances to 10 to the minus 16 or so centimeters. And one can actually imagine the LHC, and I will talk more about that, as a super microscope to look at these very small distances. So what were really the very big questions already in the 80s, which initiated the project? Well, this was to understand and complete in a certain way the standard model of particle physics. And I just will introduce in one slide the terminology which I will use. We have in the standard model, first of all, the families of quarks and leptons, which are the constituents of matter, quarks and leptons, as I said. Then we have the carrier of the forces, the photon for the electromagnetic force, WZs for the weak force, the gluons for the strong interaction, and eventually, still an open question, the gravitation. Now, in this picture, you see here a field which relies, somehow binds all these particles. This is the so-called Higgs field, which would give us an explanation of mass. So, with other words, actually, since almost 50 years, we are looking for a manifestation of this mechanism, the Higgs mechanism, electro-weak symmetry breaking mechanism, which would give us an explanation why these elementary particles actually have a mass, and why these masses, for example, here for the quarks, they are on such different scales. The theory for that was put forward in '64 independently by different groups, in particular by Braut and Englert, by Peter Higgs, and then by a group by Guralnik, Huygens, and Kibble. And since many years, many generations of particle accelerators, one was searching for the manifestation of this mechanism. A second motivation already in the early 80s for the LHC was the search for simplifications going beyond the standard model, which leaves open a lot of problems, a lot of free parameters, and there was a very elegant formulation called supersymmetry by Julius Wess and Bruno Zumino, sitting here in the front row, which made a unification in a way of the fermions and the bosons, fermions half spin, bosons integer spin, some kind of unification of matter and forces. So it would add to our known world of particles maybe a new world of the similar particles, but with a difference in the spin of 1/2. One very attractive motivation for supersymmetry is that it could actually give a hint on a mystery in nature, which we have in the universe. Namely, we know already since the 1930s, by the way, by a countryman of mine, Fritz Zwicky, that the gravitationally acting matter in the universe, which we see in shining stars, is not enough to explain the dynamics. He saw this in terms of galaxy clusters, and then much more directly, Vera Rubin saw this in the dynamics of stars in spiral galaxies. In fact, she looked at the speed of the movement of stars as a function of the radius in this galaxy, M33. She found the speed going along this curve, and that is what would be expected if just gravitation of the visible stars would be at play only. So both concluded that there must be more matter out there which interacts gravitationally, and in fact, supersymmetric particle, namely the latest one, could be a candidate for this mysterious dark matter. We will come back to that later on in the talk. And finally, maybe another general comment to the motivation of the LHC is just to continue the quest for unification of the forces, which has been tested beautifully with electron-positron collisions to establish the electro-weak model, which unifies electromagnetism and the weak theory, and in the standard model, including also QCD, and maybe pushing the limits further, including supersymmetry and grand unification. The LHC also could give a first hint why the force, namely gravitation, is so much weaker than the three other forces. And again, at the end, I will mention some of the signatures which we could eventually observe at the LHC relevant to this question. So maybe a few historical comments how the LHC came about. In fact, the first time that one was talking about the possible collider of protons was in 1977 when people were projecting to build a large electron-positron collider, which later on came into life, called LEP. This machine was approved in 1981, and already at that time, one was thinking to make the tunnel such that it could house eventually a future machine. But the fact that these hadronic collision actually can do discovery physics, this was really convincingly demonstrated in the early 1980s with the discovery of the W and C bosons in the UA1 and UA2 experiment. And never mind what this shows, but it shows you a very distinct signature of two electrons, actually, of a Z boson decaying into two electrons. This is just 180 degrees separated, bundled energy, which are electrons. So from then on, it was clear that a very high energy hadron collider, one was trusting that this could actually be a machine to find new physics also in the future. So then, to summarize the history, in 1984, the community started discussing how to put such a machine, sketched a little bit here, into this LEP tunnel, which at that time was not yet built. So you can see one needed really a long time vision. There were intermediate studies, and in fact, it was then in 92, to make the story short, that the experiment, one of the two experiments which we are talking about today, was proposed. So it is just 20 years ago that the ATLAS experiment was proposed, and indeed, we had just a couple of weeks ago a collaboration meeting where our spokesperson was presenting a cake with 20 candles. It was a very nice historical moment to remember these old times. Now, on CERN, for the project, in fact, the key dates are 91, when the Director General of that time, who was one of the Nobel laureate for the WC discovery, Carlo Rubbia, agreed with Council that a Large Hadron Collider would be the next machine for CERN to be built. A proposal was then made in 93 to actually build the LHC, and it took CERN Council quite some time to approve the project. And it was first approved in end of 94 as a staged project with the first phase, but it was always understood that the full energy machine could be built if there would be more participation also from partners outside of Europe. So in the years then 95, 96, 97, a lot of negotiation took place with countries outside of Europe, in particular also the US. And in fact, in December 97, the project as we know it now for LHC was approved. This is a picture showing the Director General of that time with the two US representatives, Martha Krebs from Berkeley and Bob Eisenstein, signing the agreement. But I would like to point out that central and really instrumental to arrive at this CERN-US cooperation agreement was George Trilling from here, sitting also in the audience. He has really led this successful negotiation in the early and mid-90s. So let me now come to the LHC. And what is the LHC? Well, in '92, it was also a pop band. And I was quite a fan of them, Les Horribles Cernettes. And I showed this. There's another picture of them. It has actually some meaning because arguably it was the first picture on the web. In the early 90s, the World Wide Web was introduced, invented at CERN by Berners-Lee, who at that time was a staff member at CERN. And then just something like 2 years later, the first picture was actually put on the web. Nowadays, for us, it's so common to use the web and get pictures as much as we want. But of course, the LHC is something else. It is the Large Hadron Collider in a 27-kilometer tunnel, typically about 100 meters underground, near the city of Geneva, which is about here. This is the Lake of Geneva. We sometimes say, well, here on the airstrip, we accelerate airplanes, and here we accelerate particles. Now, in fact, one has to realize that within less than a century, the evolution of particle accelerators has made enormous steps. And in fact, again, Berkeley was, of course, pioneering, in particular, the first accelerator by Ernest Lawrence here in the 1930s. It's a bigger object, roughly when I was born. So it's really a big step to the machine we have now. This is a picture looking into the tunnel before all the elements were joined. These are superconducting magnets with two beams counter-rotating here about 20 centimeters apart from each other. This is also a picture of the project leader who constructed this machine, Lyndon Evans. Now, the magnets are to guide the particles on their racetrack around the 27-kilometer ring. You need some elements to accelerate them. These are supraconducting cavities, are they called. What they do is, every time when particle bunches pass by, there is an electromagnetic field such that they get a little kick, a little bit accelerated. Actually, the particles race around here 11,000 times a second. So this has to be, of course, all in phase. Then, near the points where the particles are brought into collision, they are focalized such that we get a lot of collisions because we look at events which are very rare. And you see here such focalizing elements. And the other thing you see that clearly also on the machine, there was some participation of non-European countries. In particular, these elements here were built by Fermilab and KEK. KEK is a laboratory in Japan, but a very delicate part of these magnets was also built under the responsibility of the Lawrence Berkeley National Lab. And the purpose of these magnets is really to focalize the beam at the point where they are brought on collision course. So in a schema, simplified, what happens is particles are pre-accelerated by smaller accelerators faster and faster, brought essentially to the speed of light, and then they are brought into a collision where the instruments, the experiments, and we'll talk about that, are located. So that's the principle. Now, in practice, they are not just two particles, they are packages, bunches of particles, something ultimately of the order of 2,800 in one direction, 2,800 in the other direction, in each bunch, about 10 to the 11 particles, so which are then brought into collision. We need a lot of collisions because only 1 in 10 to the 13 collision typically will give us a detectable candidate, for example, for a Higgs boson. So the particles are brought into collision at 4 points on this ring in 2 big general purpose detectors, and I will show more about that, and in 2 other places where some specialized experiments are located. So there are 4 big experiments on the ring. And these 4 detectors are were built and operated by large collaborations, as we call that. Atlas and CMS, each one about 3,000 physicists, almost 200 universities, and many, many countries collaborating. Just some pictures quickly on the experiment. This is the smallest one. It's called LHCb. It's hard to see. It's actually just a spectrometer in one direction of the beam after the collision point. This is overlaying a schematic. I will not talk about that further. Another picture is from ALICE. ALICE is an experiment looking in particular at heavy ion collisions. This is already bigger, as you can see. This is a human scale. And again, I will not talk more about that. And I will talk now for the Higgs physics about the CMS and in particular the ATLAS experiment. This is a sketch of the CMS experiment, which has a particular interesting part, namely here a 4 Tesla solenoid. You all know from studies maybe what a solenoid is. This one is the biggest one ever built. Just to show you a little bit the scale, these are the coil windings, and this is the solenoid when it was introduced into its cryostat. It's a 4 Tesla superconducting coil, which provides a strong magnetic field to measure the trajectories of the particles emerging from the interaction point. And that is a picture giving you a glimpse of the complexity before the end caps were closed. This was in summer 2008. Let me now, sorry, this is the wrong direction. Let me now talk about more about the ATLAS experiment. That is where I'm most familiar with. And actually, in the ATLAS experiment, we collaborate since '93 after the termination of the American project in Texas. We have some 40 US groups, and 600 scientists roughly from the US, which are working on ATLAS. As you can see, it is really a world-spanning collaboration. And maybe just to give you an idea, these 3,000 physicists, well, there are a lot of young people working on them. As you can see, this is the age distribution. So coming back to the graduate and graduate students, they certainly, if one would even wait with the work they do, I guess they would even peak more in these low age bins. Now, ATLAS is installed in an underground cavern on the LHC. So these are the 2 beams which are brought into collision here in the middle. It's a hall which is as big as you could put in the Arc de Triomphe of Paris, about 50 meter long, about 40 meter in height. And the floor is about 100 meter underground. And the detector itself is a very big instrument, about 25 meter diameter, 45 meter in length, and has different layers of particle detectors around the interaction point. Now, just to give you an impression of the large pieces, this is the hole as it looked like in 2004 when we started installing coils of a supraconducting toroid magnet system. These are coils which are 26 meter long, 5 meter in that direction, and they carry supraconductor, in total something like 80 kilometers of supraconductor, which have a current of about 20 kiloamps. So they produce a very large, strong magnetic field for measuring the particles which come to the outside of the detectors, which are muons. This is maybe the picture, this was in 2005, which is maybe most known from Atlas, when just the toroid was installed, but not yet the other detector parts. And just to tell you, we were rather surprised when we actually saw that this picture has not only inspired us as physicists, but also, for example, was a stage setting for an opera, which was first shown in Valencia, but then also in other places. Now, this is another picture later on in 2007, when particle detectors were installed, and the end cap was ready to be driven into the cylindrical part. Now, the Berkeley team has played a very major role in the construction of this instrument, in particular on the part which sits just around the interaction point where the density of particles is highest, and this was certainly a technological challenging task. In fact, these are silicon strip detectors, 6 million channels and some 80 million channels of pixel detectors. And this is a picture of such a pixel assembly, which was done here in Berkeley. And then it actually made a very famous travel from Berkeley to CERN. You can see flying business class, better treated than physicists. This is a picture in June 2007 of the Berkeley pixel crew with the pixel detector in the background, ready for installation. And let me maybe point out that people who have built the instrument, of course, they are also very much involved in the physics now. For example, Kevin Einsweiler is the physics coordinator of the experiment, and Beate Heinemann is the deputy spokesperson-elect, so the highest managerial role of guiding the science program of Atlas. This June 2007 was a busy month because just also we had a visit of Stephen Chu at that moment when Atlas was still open. And then only a few weeks later, this pixel detector was lowered into the underground and inserted finally in the experiment. Okay, let me now jump to the operation of the LHC. 2009, end of November, there was a big excitement in the control room. Again, you see some prominent LBL people here and CAL people in the control room. And what people are so happy pointing at was really the very first collision event at the LHC, seeing tracks coming from just in the part of the detector, signs of a collision. Then we have started accumulating data in 2010, something which we call in our units 50 inverse picobarn of integrated luminosity. You don't really need to think too much about that. In the year 2011, we have increased the accumulation of data by more than a factor of 100. These are the units we're talking now, femtobarns, inverse femtobarns. And just to tell you what this means roughly, we have looked at this huge number of collisions in 2011 with this integrated luminosity. And since then, the experiment has even worked better, as I will show. And however, I want to point out that a lot of the physics I'm going to show come really from this last year's run, 2011. We also collide sometimes heavy ion in the LHC. This is just showing you the accumulated amount of data, again, in these inverse cross-section units. What this always shows is the delivered, the upward curve, and the lower curve, the data used actually and accumulated by the experiment. So you can see it's a large fraction is actually used. The experiment I mentioned has a lot of channels, in particular in the pixels and in the silicon strips, 80 million, 6 million. As you can see, a large fraction is working, typically more than 96%, in many cases almost 100%, which I think in such a complex instrument is quite an important achievement. So this year now, the machine runs really superbly and delivers a lot of collision. This shows you a typical sequence. We have colliding beams. Then it takes a few hours to dump the beams, set up the machine again, and we collide again for a couple of hours and so on. And the integrated luminosity today is already about 4 or 5 times as much as last year. And again, as you can see, with a very good efficiency in accumulating the data, and also with a very good efficiency actually to have the data quality ascertained for use to make physics analysis at the end. So what really counts is the efficiency to take the data, this here, times the efficiency that the quality is usable for physics. And the use for physics about 90% of all the collisions which are delivered by the LHC, which again is a very good achievement, and of course very important if you look for rare things. The fantastic operation of the LHC also poses a lot of challenges. In fact, per crossing of bunches, not only one pair of proton collides, but on average many more, like 20 to 30 pairs. And so you have, for example, an interesting event is here are just the inner tracks of a Z into mu plus mu minus decay, but you have to find this out of a mess of some 25 other interactions. And here this powerful silicon tracking system is really working very nicely and allows us to do that. The other element, which I want just shortly to mention, to arrive at the physics results, which I will come to now, is the computing system. And in order to deal with this large amount of events, typically 500 per second we record, we needed to develop a highly dynamic distributed, worldwide distributed system, which is called a grid computing system, which consists of 11 big regional computer centers and then something like more than 100 smaller but still large computer centers worldwide. And I can say that in the US, the main Tier 1 center is in Brookhaven and works very efficiently together with several Tier 2 centers, one also here in California. So let me now come to the physics highlights. And of course, I have to be very selective because both the ATLAS and the CMS experiment have already published more than, by now, more than 400 papers. And it's obviously not possible to cover all of that. And just to give you the reference, all these papers are, and also contributions to conferences, they are publicly available on the web. So I will present data a little bit according to their cross-section. That means according to the, the probability that they occur. And you can see this is a logarithmic scale. I mean, the normal interactions, we have something like several 100 million collisions per second in elastic collisions. Then we have p-quark production, maybe a factor of 100 to 1,000 below that. Then we have the WZs, top, several orders of magnitude less frequent. And then we come even much lower to the interesting new physics. And I will follow this path a bit by first talking about, very briefly, general event properties, which we have to understand because this is our background to any new searches. And what these graphs, now a bit more for the experts, show is, for example, the multiplicity, the number of charged particles which are produced in the collisions which spray into the central part of the experiments. And you can see now at the LHC, this is rising compared to lower energy machines. Maybe another proof that the experiment is well understood and produces physics. This shows here some resonances, which were the topic of physics decades of years ago. For example, here a cascade particle with a very beautiful peak recognizable, or here a beam meson, the BS meson, very nicely recognizable over the background. Maybe a summary of the history, in a way, of physics. Particle physics can be given by looking at mu plus, mu minus final states and looking at their parent invariant mass. And so this is a very simple signature. And we see here particles like the Z we have been talking about before, 1983, when it was discovered. But earlier, for example, the Upsilon families discovered at Fermilab, or the shape psi co-discovered at the SLAC linear collider in 1974. So these just come in a way online, we can observe them. Of course, we are very interested what happens here in a new domain. So let me talk a little bit about what we call the standard model physics candles. And the most easy one to find are really the Z into mu plus mu minus or E plus E minus, and the W, which decays just in a muon or an electron, and then on the opposite, a neutrino. So this is an event display with two muons, as it can be seen in the CMS detector, or a W with an electron and nothing opposite, because the neutrino leaves the detector without any trace in the ATLAS experiment. And we have actually millions of these events to study. The signals are standing out over the background very clearly. This is the C peak in E plus E minus, or the C peak in mu plus mu minus, and you really have to go into a logarithmic scale in order to show the background, which is many orders of magnitude below the signal. So this is a very clean signature, and if we're talking and looking back, it was, this is just like a miracle for people who have been involved in the discovery of the W or C, which was much more background and only very few events. Similarly for the W, and I will not talk about that more, just to show you that indeed the cross-section, the probability of W production, for example, now at the LHC energy, has been measured and can be compared with QCD calculations, and you see there is a pretty good agreement within the errors, which means that there is a proof of understanding of the instruments for this type of physics. There are three families of quarks and leptons. I have so far only mentioned the muons and electrons, but there is also the taus. The taus are a bit more difficult. This is, nevertheless, they can be cleanly identified. For example, this is a Z into tau plus, tau minus decay. One of the taus itself decays then in a muon and 2 neutrinos, and the other tau, for example, in 3 charge tracks and a neutrino. And this is, again, such an event display. It is characterized by quite a lot of what is shown here in dot, by missing energy because of these many neutrinos in the event. We were talking about jets, and this is an example of a very hard collision where quarks, gluons collide and then make sprays of particles. In this case, the invariant mass of the which one could attribute to these two partons making these sprays is about 4 TeV, which is twice the total collision energy of the previous P by P collider at Fermilab. And you can see these events are very clearly recognizable with a lot of bundled energy in 2 directions, for example. One can look at the cross-section, again, as a function of the PT, transverse momentum of these jets now extending to further than 1 TeV. For the experts, this plot shows how this cross-section has increased now at the LHC compared to the Tevatron and compared to the UA1, UA2 experiments some 30 years ago. We have talked about Ws, we have talked about jets. Now, in order to understand really the dynamics of the collision, it's very important there are events where a W and jets are produced in the collision. And just as one example of how well the data are described by quantum chromodynamics, QCD calculations, this is a very detailed plot of W production together with 1 jet, 2 jets, 3 jets, 4 jets, then as a function of the jet PT. And the points are the data. And if you take just, for example, the ratio of the theory over the data, which ideally should be 1, you see the data points, and you see how much the theory, deviates, or the data deviates from the theory. Either way, you can turn it, and you can see this is a very good agreement at the level of 20% or so. So this is a very important test, again, that we understand this type of reactions. So let us look at the last candle, in a way, of the standard model, which is the production of the top quark. The top quark was discovered at the Fermilab Hadron Collider. It's the heaviest particle we know so far. It's about 175 GeV in mass, almost 200 times the mass of the proton. And the top is a very interesting object. It's produced mainly in T-bar events. And then the top decays all the time, essentially, into a B quark and a W. The W, okay, that we have already seen, can decay in electron, muon, and a neutrino, or it can also decay in two quarks, giving jets. And the B is a heavy quark which has a finite lifetime. So we can measure actually a bit its decay path. Well, there is also missing transverse energy involved because of the neutrinos. And just to show you one very clean example of such a TT-bar event, where both in the chain the W decay in a lepton and a neutrino, in this case in a muon and into an electron, then there is missing transverse energy. And if we zoom in, we see that there are also two vertices which are not coming exactly from the interaction point, but fraction of millimeter away from it, which are the signatures from the B quarks. And this gives then the possibility to measure the fraction of such events. And if we see, for example, here, events with two leptons and, for example, two such displaced vertices from the jets, B jets, we see that we have a very nice signal over what we know here, shown in color, is the background. And again, this has then served to measure, in a way, the cross-section of TT-bar production at now the LHC energy. These are the points. The yellow and the blue are the QCD calculations. And as you can see, for example, here, these are two different QCD calculations. These are the measurements. Again, there is excellent agreement between the measurement and the prediction. Finally, for the standard model, a last test going down in our cross-section in smaller and smaller probabilities is the production together of a W and a Z, or of two Ws, two Zs. This is such an event where we have simultaneous production of a W and a Z, the W decaying into an electron and a neutrino, the Z into mu plus, mu minus. And such events, again, have been studied and their cross-section measured. And I come finally to this summary graphic, which shows you here the cross-section probability for different processes, WZ production, TT-bar, and so on. As I mentioned just now, this boson production. And the fact that we reproduce the expectation from the standard model so well, as you can see, the bars are the prediction, the points are the measurements, gives us confidence that we're ready now to look for new physics. And let me say that I was this spring giving talk in China, and people told me, yes, we are in the year of the dragon, which is a very good year and a very lucky year. And I think it's true, because I think it will be also remembered as the year of the Higgs boson. And in fact, this is a type of event we are looking at for the Higgs boson, decaying in fact, into a Z, which in turn decays into mu plus mu minus, and another C, which decays here into E plus C minus. And we are looking for such event signatures among many others for the Higgs boson search. And what I want to say for the Higgs boson search, it's not just one final signature we're looking at. There are many possibilities it can decay into. For example, the Higgs can decay in WW, it can decay in ZZ, but it can also decay in taus, in photons, and then in particular into BB bar and other fermions, TT bar and so on. And characteristic for the Higgs is that its coupling is proportional to the mass of the fermions involved. And that is what we have to test in a way. And well, up to recently, we had, of course, to test the whole. We did not know what is the mass of the Higgs, so there are different mass ranges, and this is just indicating which of the different decay modes is most promising to find the Higgs. So let me show you now two examples of many searches. The first one looking for decays where the Higgs decays into two Z's. One may be, we call this a virtual one, not at the real Z mass, but below it. And then the Z decaying either into two electrons or two muons. So you have these three combinations of possibilities. And what you see here is actually the data over all the mass range, the data up to this summer. In red is what we know from continuous CC production, which I have just mentioned before. This is ordinary standard model production. And then superimposed are some peaks where, how would we see actually a Higgs boson? And we are looking for some indication of data above the red continuous background. And if we zoom in here, we see that actually, indeed, we start having a statistically significant indication of Higgs boson at this mass. Not yet many events, and in fact, it can be quantified, and I will show you later on the statistical value of that. Just to say, there are a handful of events. In total, something like 13, and from the known backgrounds, we would expect something like 5 or so. The other channel which I want to show you is to look for the Higgs decaying into two photons. This is a rare decay, but again, it allows us to fully reconstruct eventually a mass peak. And the pattern of events we are looking at are events where back to back we have energy deposition in the electromagnetic calorimeter, which measures electrons and photons. But there is no track in the tracking system which you would expect if you would have, for example, an electron. So this is the type of events we are looking at. And they are rare. We have to distinguish them from any type of background fluctuations. Now, like in the ZZ mode, there are ordinary processes which give us two photons, but they would not accumulate at the given mass. They can be at any mass. And in fact, what they give a mass spectrum. And I will skip some of the thing and just show you what we actually observe. We observe a smooth distribution of, as a function of the mass, of the data, except at about 125 GeV, where we see an accumulation of events. As you can see, the signal over the background is not very large. It's about only 2%. So you need a lot of data really to start building up a significant peak that you can distinguish it from any possible fluctuation. But there is no doubt that here a resonance signal is being observed. And this can be quantified by making a statistical analysis asking the question, what is the probability that the background, without any Higgs boson, would fluctuate and give you such a peak? And this is expressed usually in something which is called the local p-value. And if you take both the photon channel, the ZZ channel, and eventually other decay channels together, you see that at some point, you see an excess of events where the probability would be something like 10 to the minus 9 that it is just a background fluctuation. So what you also see is what would you expect as a function of the mass for a standard model Higgs? We would expect to see a background fluctuation probability 10 to the minus 7 or about. Well, we are a bit lucky. We see a little bit more, a bigger excess. If we zoom in, this is shown once more, and we see clearly a strong signal at about 125 GeV. And that was essentially the basis of the great joy on 4th of July, when our spokesperson met Peter Higgs, who was saying that for him it's really unbelievable that this happens in his lifetime. ATLAS is one experiment. CMS is the other experiment looking for the Higgs signal. And I just show you here a summary plot. Also, they see a very clear accumulation of data, for example, in the channel gamma-gamma. And again, if I show this local P0 plot, you see the signal for the Higgs in gamma-gamma. You also see the signal, for example, in the Higgs in ZZ, and there are other channels added to it. So there's no doubt two experiments independently have observed a resonance. And this then gave rise to the rather important first discovery papers jointly by the ATLAS and the CMS experiments, which were published at the end of July. And I must say that in a way, really a dream from long time ago became true, and actually much faster. We were predicting, this was still in the 90s, that if the mass is low, we should see a signal in green in the gamma-gamma and in the ZZ. This is the significance. And if we look at the plot now, clearly we do see, in fact, a nice signal. This is similar as I showed before. It's just expressed in standard deviations as a function of the mass. So you see over the whole mass, you have some fluctuations up and down, typically between 0 and 1.5 sigma or so, nothing spectacular, but then you have 6 standard deviation, a signal at 125 GeV. So clearly the question is, what is it? Is it the standard model Higgs? Well, one can express this with a so-called signal strength parameter, which would be 1 for the standard model. And what this shows for ATLAS and for CMS is the measurement in different decay modes. And certainly within these statistical errors, this is well compatible with 1 so far. However, of course, it is really now the burning question, is it one or is it not? Well, we see, for example, a tantalizing thing that in the Higgs in gamma-gamma, we seem to see more signal in Atlas. Well, only 1.5 sigma, so not much more, a little bit more than expected in CMS. And we are very keen to see with the new data how this will look like. Why is this so interesting? Well, the standard model prediction for these channels, the Higgs in gamma-gamma, is related to the known particles, which we call here in these loop diagrams. Now, for example, the W and the T, it couples preferentially to high mass particles. Now, if it is more than one, if these measurements really would turn out to be correct, this could give us an indirect hint that there must be other particles around which contribute to this loop. Okay, so let me make a few examples of physics beyond the standard model. And the first thing which I want to address very briefly is the search for supersymmetry. That's a very complex business, and about more than almost maybe 1/3 of the papers of Atlas and CMS actually deal with this type of searches. Basically, what one looks at are event topologies where you have in the final states, in the decay chains of supersymmetric gluon, here for example of a gluino, you have quarks, you have leptons, and then at the end you always end up with what is called the lightest supersymmetric particle, neutralino it's called, which leaves the detector without any traces, a little bit like the neutrino. And it's in fact this neutral, stable, lightest supersymmetric particle which could be a candidate for the dark matter which has been produced, that is 10 to the minus 10 seconds after the Big Bang, and then still is around, which has remained after the universe started cooling down, and it has accumulated in, for example, the galaxies and so. So the typical signals we're looking at are, we're looking at event distributions of these guys here, and including then missing transverse energy. And we compare that with the background we predict and measure from the standard model. So we're looking in the tails of distribution, essentially in variables which are dominated by missing transverse energy. So that's a basic principle, and I will not go into much detail. I'll just show you one example of such experimental distribution. We can look at such a distribution in a region where we know there should be no supersymmetric particle produced. And indeed, the data are perfectly in agreement with all the known backgrounds. And then we go into a region where we would expect a tail, as it is shown here, for example, in this dotted histogram, if there would be supersymmetric particles produced. But disappointingly, maybe the data again is completely compatible with what we know from the standard model backgrounds. So the fact that we do not see any excess, we can then translate into an upper limit of the cross-section of the probability that, for example, such a signal would occur. And we can confront that afterwards with what is predicted by supersymmetric models. And there are many models, but and this, of course, if the supersymmetric model in question, which we're looking at, would have predicted a cross-section which is larger than what we can exclude here, then we can say, well, we exclude this region of that supersymmetric model. And that's exactly such a plot. In fact, if we look in a plane of gluino mass, in this case, and quark masses, we can say that all the cross-sections, all the masses on the left side of this curve is excluded. There are some statistical indications here, data and what we would expect or so, but never mind. This shows you that, for example, for equal gluino and quark masses, we would exclude something like of the order of 1.5 TeV objects in this particular model. Now, I have shown you the one with the highest cross-section. There are many processes of quark and gluino production, then supersymmetric T-bar production, Teichinos, gluino production, and so on, which have smaller cross-section. And of course, naturally, the limits on these ones are much weaker. And I will just tell for the experts that the currently most popular models of supersymmetry, they would actually predict that the top quarks would be the most important one to look at, would be the lightest one, is third generation. And this is a plot where we plot actually the top quark mass and the neutralino mass. And these red, these colorful regions, they are excluded, but there is still a lot of room left for such supersymmetric productions. So these searches, of course, will go on for a long time, and are still one of the main motivation for the LHC. This is just to give you a summary of, as I said, many papers are looking at many different of these processes. This is from Atlas, but similar thing is available from CMS. Maybe a few more examples, and then I stop in a few minutes. An easy search is to look for heavy brothers and sisters, for example, of the Z, by just looking into E plus E minus or mu plus mu minus invariant mass. And that is how a heavy C prime, for example, of 1.5 TeV or 2 TeV would show up. Well, the data certainly do not support this yet. Again, we can then translate this in an upper limit of a cross-section and confront this cross-section with predictions as a function of the mass. For example, for C primes which would behave, they're called sequential standard model C primes. This is our limit. These are the prediction. So we can say, well, all the predictions for cross-sections above this mass here, below this mass are excluded, and we can then set here a lower mass limit of typically 2.5 TeV in this case. Or, for example, in the case of graviton models, these are Randall and Raman Sundrum model for gravitons. Again, this gives you different exclusion limit depending on parameters in their models. I understand both Sundrum and Randall, they were postdocs here at Berkeley. And they're very interested in, of course, in these experiments at the LHC, what's going on. Another example to look at exotic physics is looking into the mass distribution of two photons. And now we're not looking at the Higgs, which sits down here, but again at the high tail. And certainly we have not found any resonance yet again, this poses some upper limits. I will skip one or two other examples. Maybe I end with one which would have been very spectacular, but we haven't yet observed this. This is looking for extra dimension in models brought forward by Stephen Hawking, which would predict that some microscopic black holes are produced, which then evaporate immediately, 10 to the minus 25 seconds or so, typically. But they would be very spectacular. This is a simulation, because in a kind of democratic way, you would have leptons and jets in the event, and many of them. So we are looking for such topologies. This is, for example, an event with 9 jets in the CMS experiment. And we are looking whether they occur more frequently than what is predicted by the standard model backgrounds. And again, the game is to look at deviations, for example, here in the scalar sum of all these transverse energies of jets and electrons, muons, photons. As you can see, there are none, and again, this at this moment allows us then to pose upper limits on the cross-section and therefore lower limits on the masses. And this is just to show you a huge collection of searches for extra dimensions, for example, for leptoquarks, for new quarks, for excited fermions, and so on, typically above the 1 TeV mass scale. So I think this was a very restricted selection, of course, of physics results from the LHC, from ATLAS and CMS. But we are only at the beginning of the lifetime of the LHC. We are now finishing the run at 7 and at 8 TeV. This has brought us the discovery of Higgs-like boson. I think this is a very exciting first step. We will then have a shutdown of the machine to go from the 8 TeV to the design energy of 14 or close to 14 TeV, starting again taking data at the end of 2014. And we will increase the luminosity, the intensity of the beams, until about 2020 in the present configuration of the machine. And then we will, in the meantime, prepare the machine and the experiments for another decade of data taking at even higher intensity. This means some upgrade of part of the machine and part of the instruments. So I think we have really exciting times for discovery still ahead of us. We have just made the first step. And I would like to end by saying that, well, almost 20 years of working with the Berkeley colleagues and friends in ATLAS was a real pleasure. And I think we're looking forward for a bright future of this enterprise for at least another 15 years. So thank you very much.
Thank you. That was marvelous. And now we will take questions.
I've written this down to get it right. This is a question. All man-made vacuums have a small background pressure, including those in the particle accelerators. It turns out that if the background pressure in a particle accelerator is below a critical value, the beam current goes to 0, a fact not discussed and explained in the physics literature. In order to create the Higgs boson, I'm wondering what background gas was used. Was it uranium octachloride and/or uranium octafluoride?
I'm not 100% sure that I understand your question. I mean, there is a vacuum in the beam pipe, which is of the order, well, which is highest at the places where the beams collide, because if there would be some residual gas, of course, this could give spurious collisions, which would produce a background in the experiments. And but it's true that this machine, of course, only operates if there is a high vacuum all along the ring, particularly high at the places where the detectors are installed.
The question is, why did the beam current go to zero if the background vacuum is below a certain critical value? This is according to Livingston in his textbook. He presents graphs at this time. And so therefore, it must be important. This is missing physics there.
Maybe for a practical thing, I can tell you, if the vacuum at some places would start deteriorating, the beams are always extracted and dumped. So I think the experiment, what you say, is not really being made, because that would be too dangerous also for the equipment, because you could destroy the equipment if you start blowing up the beam and hitting the vacuum pipes and so on.
Thanks. Well, you see something for which you've been able to measure the mass, right? But do you have any other properties?
Well,
you must know it's a boson, probably, and
yes,
you know its spin.
So we know that it is a
boson
boson because it decays in 2 photons.
Are you sure you caught everything with those 2 photons?
Yes, I think that we are pretty sure, yes. And if you would not take everything, then of course you would not expect it to accumulate at the given mass value. If there would be massive third particles involved which carry away a lot of energy or so. So I think that we are pretty sure, yes. Now, what else? We measure the different branching fractions in a way. Of course, still with rather large error bars. And that will be very important to establish that it is a Higgs boson. That is. Then the next thing which we also will measure is its spin. It could be spin 0, as it should be, if it's a Higgs boson, or it could eventually be spin 2. Nobody would expect that. But from the angular distributions, we will be able to nail this down pretty soon. In fact, with the data of this year's run, the full data and the 2 experiments, I think we should be able to exclude spin 2 at something like 4 or 5 sigmas already. So this is certainly will be one of the most important things coming out with the new data.
Let's see, there's way over here, and then I'll come back.
Thank you, and thank you for your lecture. My question has to do with the volume of data that you get and the automation that you must have in order to analyze it. When you have your uncertainty bars on your experiment, various data, what is included within that uncertainty bar and what is excluded?
Well, at this moment, the error is really, for the Higgs boson, the amount of, is really the statistical error. So plus, there are systematic errors which go in, but it's many of these measurements are dominated just by the statistics. There are, of course, in establishing for example, the cross-section, you need to know very well how efficient you are actually to collect the data, trigger efficiency in our language or so. These are studied very carefully, very often using data itself. And of course, errors or uncertainties in these considerations are also included. It depends now to what you refer to. There are measurements where also systematic theoretical uncertainties are included. But just to give you, for example, I had on one transparency is the masses of these peaks. And what we have quoted is, in this case, separately, the purely statistical error coming from the fluctuation of the data, but then also systematic errors. For example, in the Higgs in gamma-gamma, you have to parameterize the shape of the background, which we measure with the data, but still it has there are some uncertainties how you parameterize it, so this is then put into the systematic errors. So your question is not a simple one to answer. I mean, it depends on which of the measurement you refer to. But for the Higgs, most of it is dominated by the statistics at this moment.
Could you give me some kind of a motivation why we should expect a facility that the Higgs seems to have for decaying into the weak mediators, the Z and the W?
Excuse me, I did not catch the question.
The Higgs seems to want to decay into Z and W and also gamma, so the mediating particles for the weak field and also for the electromagnetic field. Why? Is it because it's a boson? Why does the Higgs like to decay into Z's and W's and gammas?
Yeah,
they're all mediators.
Well, it's a boson, so it decays into the W pairs and the Z pairs. Yes, you're right. This is.
I think actually, it's a good question for those of us who are not experts. Let's see, back here and then right there.
I'd just like to know what is the expected mass of the Higgs particle that you're looking for, and what's the comparison between the gamma decay and that decay that you would get in something like a pair annihilation between electron positron situation?
Well, there is no prediction really of the mass of the Higgs. I mean, what we observe is consistently in both experiments that we have a particle at around 125, 126 GeV. This is well compatible with actually indirect measurements from what we know from the standard model from other measurements, but there was no prediction. It could have been the experimental lower limit was about 115 GeV set up directly by the electron-positron collider lab, but then it could have had all the masses up to 1 TeV essentially, and the data at this moment clearly indicate the mass, fix the mass to something like 125, 126 GeV. So your question is if you would have now an electron-positron collider, for example, you would have to tune the energy, the collision energy around this mass, and you should see, in fact, the Higgs production. It's not how you would really do it. You would look at in an electron-positron collider, because the cross-section for that is very small. You would look at associate production of a Higgs and the Z0. That's why you probably would not run just at 125 GeV, but you would run, because there you don't see anything, the cross-section is so small. You would have to make this associate production. But that's a different issue.
I'm curious as to how many cumulative photon gamma-gamma channel events you had in 2011 and 2012, both CMS and Atlas combined.
Yeah, it was on a transparency. It was of the order of 100. And the signal over background is about 2% only. Maybe I can actually find back the transparency, which would give you even the number. If I manage to go backwards. Maybe you can take another question in the meantime.
Sure. And I think we'll I see like one here, I think one, two over there, and then we'll wrap it up after that.
Hi, I have a non-technical question, actually. You spoke quite a bit about the vision that was required in order to make the LHC a reality. What do you see for students like myself as physics beyond the LHC?
I did not, sorry to say, not catch the first part of your question. I want not to, yeah.
I was just saying you spoke quite a bit about what it took to make the LHC possible and the amount of time and investment. What do you see as physics beyond the LHC for the students that are about my age?
Oh, well, so first of all, I think we have only started really a very small step in the exploration of the potential of the LHC. I think all the searches for physics beyond the standard model are still open, and I try to indicate this, for example, in supersymmetry. There is still a lot of possibilities, but then clearly we also have to think what comes after the LHC. And indeed, the communities in the US, but also particularly in Europe at this moment, are engaged in what is called a discussion on the strategy for the roadmap of particle physics. And there are different possibilities among them. For example, a Hadron Collider, which would go well above this 14 TeV collision energy, which would require a new large tunnel. One is talking about 80-kilometer tunnel or so. This is something to dream maybe in, maybe in the 2040 or so. This could be running. Other possibilities are electron-positron collisions, not only at the relatively low energy to investigate in great detail the Higgs boson particle, but to go beyond that, maybe up to 3-4 TeV collision energy. Or other dreams are to look at the muon collider, which also would be very interesting, actually, because this you could do with on a smaller site. Has many other highly challenging aspects, but that's certainly something it's worthwhile investigating and developing the technologies. So there are several roads open, and indeed there is discussion in the community going on to make some a priority, what should be really focalized for the next generation of accelerators.
I think you pulled that up in order to answer a previous question.
In fact, it doesn't tell you the number of events. I just realized on this slide. But it tells you that the signal over background is only about 2%, and you can read off here how many events there are per bin. So you take 2% of 2,000 typically in these bins, which, gives you this about 100 events or so I was mentioning, if you take a few bins.
Okay, I think I'm going to, we'll take one last question here because he's had his hand up for a while.
Okay, I can see a fairly strong signal there at 125 GeV, something which you have confidence in. Are there any other tantalizing hints anywhere else in the energy range that you're measuring that might hint when you ramp up to 14 GeV or TeV that you might find other signals of Higgs-like particles?
Well, of course, as I said, we also see it in the 4 lepton channels, albeit with very small numbers at this moment. Now, you're asking if we see anything at other masses. The answer is no, not on the level what we would expect for a Higgs particle, standard model Higgs, for example, at 400 GeV or so. This we exclude even much stronger than 95%, at 99% or so. So far, so there's no other hint. The only region is really around here where we cannot exclude the standard model Higgs. In fact, we do see it.
Well, I think we will call it. I know there was one more question, but maybe we'll let you come up and ask directly. And I guess I just want to speak for most of us in the audience to say there's something truly spectacular about the idea that people can make up theories for the, for the antiproton, for the positron, and now for the Higgs, that they, from most of our perspectives, sort of make these things up, and then they're actually there. So thank you for the talk.
Thank you very much.